So, welcome to the 15th lecture, that is tutorial 3. We will see some problem solving on equivalent voltage and current concepts in waveguide and on scattering parameters. The first problem is determine the equivalent voltage and current for TEM0 mode fields in a rectangular waveguide. We have seen how to do it. Now, just look at the TEM0 mode. Transverse electric means Ez is equal to 0 and Hz, this is the generic form. A and B are the dimensions of the cross section of the rectangular waveguide. So, if you write TM0 mode waves fields, the transverse fields will be Ey and Hx plus. Incident fields, obviously there are also the reflected fields. Now, Ui plus can be written in this form. So, that we are saying that there is an amplitude part, then this is the eigenfunction part, this is the jet propagation part. Hx plus also like this, where this propagation constant or phase constant, since we are assuming lossless line, gamma is j beta. So, beta for M0 mode is like this. Now, this M plus is this is the constant and Bm plus is like this. Okay. So, now let us define, as we said that the electric field and voltage should be proportional. So, that proportionality constant, let us say C1. So, this is a voltage side quantity that we are making proportional to Vm plus, the magnitude of the voltage wave, and Vm plus was the magnetic field part. So, that we are making proportional to the current. This is the proportionality constant is C2. So, this C1, C2 value finally we will have to find. Now, equivalent voltage and currents are like this. Now, enforce the power equivalence. So, first find out from the field ones with these definitions what is the power, incident power. So, all the steps are done for you, pointing vector, then integration over the guide. S means the transverse cross section of the guide, that means for a rectangular waveguide it is from the x is from 0 to a, y goes from 0 to b. So, if you do that, now that we have done here, that these are the thing, and this should be equal to the average power, that was the power equivalence part, half Vm plus Im plus star. So, if you equate that to, you get this relation C1 C2 star is equal to minus AB by 2. Now, C1 and C2 are constant and GL. So, C2 star will be equal to C2, that means C1 C2 product is minus AB by 2. This is one equation. So, we are calling it equation number 1. Then the next part is impedance equivalence. So, impedance is Vm plus by Im plus. We said we had two choices, either to make it equal to TM0 mode wave impedance or equal to 1. We are taking the second one, let us say that this is equal to 1. So, that makes our this thing 1. Now, Am plus and Bm plus, their relationship is by ZTEM0. Note this minus because of the power flow, that always E y and H x from their standard one should be opposite to other, so that the power can flow, because y cross x that itself is negative, another negative is required, that is why, so that incident wave power we are assuming flowing in the positive z direction. So, this minus. So, that if you put, then C 1 by C 2 will be this 1 minus 1 by eta, eta is the intrinsic impedance divided by this quantity. So, you have now two equations for C 1 and C 2, two unknowns C 1 C 2, two equations, two unknowns. So, you can solve, if you solve you get C 1 is this and C 2 is this. So, depending on T m 0 you have, these are the solutions. So, this is simple, that once we get C 1 and C 2 we can write as written on. So, this so once you know C 1 C 2 you can describe V z for T m 0 mode, V m plus by C 1, you know this value, this plus this. Okay. So, this is the description, C 1 C 2 will come from there, that is all. Now, proceed to the second problem. So, we have seen how to define voltage and current. Now, scattering parameters. Suppose scattering parameter here is, sorry, this S parameter you correct, that S parameter, there are this in the slide the values are a bit wrong. So, correct it in this slide it is given. So, a two port network scattering parameter is given. Now, determine whether the network is lossless and reciprocal or not. So, you know this is S parameter. So, we know that reciprocal it will be if S is symmetric, that means S is equal to S transpose, and lossless it will be if S is unitary. So, you will have to check that too. Then it is said that if the port 1 is terminated with match load, what is the return loss at port 2? And third part, if the port 2 is terminated with a short circuit, what is the return loss at port 1? Okay. So, let us see the first part, that here it is correctly written, the S matrix. So, for lossless network, unitary property. Now, unitary property is the any one row conjugated with itself will be equal to 1. So, rho means, let us say this row. So, 0.15 square, this conjugated dotted with conjugate of these, that means that will be 0.5 square plus 0.85 square. Now, this value turns out to be 0.75, it is not 1. So, 1 not satisfied, immediately we can say loss, the network is not lossless, that means it is a lossy network. But whether it is reciprocal, for that you see that is it symmetry, that means if I transpose this one, what I will get? Transpose of this S of t, that will be how much? Transpose means the row becomes column, so this will be the new one. Are they same? No. You see, here minus 45, 45. So, the network is not reciprocal also. So, part A is solved, that it is not unit lossless, not reciprocal. Then port 1 is match terminated. Port 1 is match terminated. So, we know that what is the return loss at port 2, that is same as S22, S22 is pointing to this. So, return loss, it is a scalar quantity. So, that is minus 20 log that reflection coefficient magnitude, and that turns to be 14 dB. So, port 2 return loss will be 14 dB when port 1 is match terminated. That is solution B, pretty simple. Now, solution C, it says that port 2 is shorted. What is the return loss at port 1? So, port 2 is shorted. Shorted means V2 minus by V2 plus, reflection coefficient is minus 1. Then V2 minus, from the general S matrix definition, we can write V2 minus is S21 V1 plus S22 V2 plus. Now, here we put this value that V2 minus is nothing but minus V2 plus, that this. So, from here I can solve for what is V2 plus, and now go to the other equation of S matrix. V1 minus is this, there put the value of V2 plus. So, everything is now in terms of V1 minus and V1 plus. So, I can take their ratio, that becomes this. So, in general this is, and the reflection coefficient is equal to, reflection coefficient on port 1 is equal to S11 minus S12 S21 by 1 plus S22. You see that reflection coefficient gamma 1 is not equal to S11. It is equal to S11 when this portion becomes 0. When that portion becomes 0, when I make that port 2 matched. If I matched port 2, nothing comes from port 2 to port 1. That time S12 becomes 0 and this whole thing becomes 0. That time it becomes equal, but not now, at least not here, because it is not match terminated. The port 2 here is shorted. So, tau 1 is this. So, now you know these values from the S matrix given, you can find these values and these. So, return loss, you can, once you know reflection coefficient, you can find the return loss. Reflection coefficient is a complex quantity, return loss is a scalar quantity, please remember that. That is why it is a magnitude of tau 1 log of that. Okay. So, we have solved the 3 parts. Given the S parameter, we can find out what is the property of the network, whether it was lossless, whether it was reciprocal. Then given various port conditions, we are asked to find reflection coefficients at various ports, that we have done. In B, it was that one port is match terminated, the other port return loss. In C, one port is shorted, other port return loss. Now, see the third problem, that S matrix of the following 2 port network. Again verify whether the network is lossless or not. Now, you see this is a purely lumped element case. So, it is easier to go to Z matrix, find this Z matrix of this is a simple symmetrical T network. You can very easily find this Z matrix, find the Z matrix, from Z matrix use the formula to find S matrix, because otherwise if you try to find S matrix, you will have to find out what is the reflection etcetera at various ones. you can do that, but comparatively that is a bit tricky, but you can just come to Z matrix. If you do, the Z matrix will be like this. This I think all of you know from your earlier knowledge how to find Z matrix of a T network. So, this will be the Z matrix. Now, once you have found Z matrix, you can use this formula S is equal to Z plus U inverse Z minus U. So, do that is simple matrix algebra, and then it will become like this. This is you can see in some books these are wrongly given, but this is the correct answer. Then the checking of whether network is lossless. So, you again apply unitary property and see it is not unitary. So, it is a lossy network, as obviously it should be, because the network was resistive. So, from that also you could have said that it should be lossy, but mathematically you will have to prove it, that is why these things. Now, a 2-port network with characteristic impedance 50 ohm is driven at both ports such that these are the various port voltage and current values. So, determine the input impedance seen at each port and find the incident and reflected voltages at each port. So, it is driven at both ports. So, impedance seen in port 1, self impedance, that will be ratio of voltage current. So, you can find Z1. Also, if you look from port 2, Z2 will be self impedance, Z2 will be this. Now, voltage V1 is V1 plus V1 minus. So, reflection coefficient at port 1 you can find by, you know, Z1, Z0, the characteristic impedance is given. So, Z1 minus Z0 by Z1 plus Z0, and if you look at impedances you can find S11 is 0. So, you can say V1 minus definitely should be 0, and so V1 plus is equal to V1. In similar fashion, you can find out that what is V2 minus S22, that is J. So, V2 minus is this, and V2 we can solve. So, V2 plus is this and V2 minus this. So, you see that problem was also solved. Now, the last problem, that determine the S matrix of a lossless transmission line. This is a distributed line. So, it is easier to find its S matrix at 1 gigahertz. Assume that line has a length 7.5 centimeter, characteristic impedance Z0. So, let us see. Transmission line has 2-port network, obviously. So, S parameter is like this, this is the definition. Now, for a 2-port network, S11 is this when port 2 is match terminated. Now, in this case, lambda, so 1 gigahertz means lambda will be 30 centimeter, and 7.5 centimeter means it is a lambda by 4 line. So, electrical length will be how much? Beta into L, beta is 2 pi by lambda, phase constant. So, beta L will be pi by 2, that means a quarter wave line, remember it has a electrical length of pi by 2, 90 degree. Now, port, how to determine for finding S11 and S21, you will have to match terminate port 2 port 2 match terminated, as we have seen, you connect a Z0 here. So, V2 plus, the moment you put Z0 here, V2 plus, that means whatever signal is coming from here, nothing is going. So, V2 plus is 0. If V2 plus does not go, V1 minus also becomes 0. So, now what is V2 minus? V2 minus is what is coming here, that is because you are exciting from here. So, this wave is coming here. So, in a transmission line of length L, a lossless transmission line of length L, a wave started from here V1 plus, after going distance L, it will add a phase of e to the power minus j beta L. So, that is what we have written, V2 minus is e to the power minus j beta L into V1 plus. Beta L, as I said, pi by 2. So, V2 minus becomes minus j V1 plus, e to the power minus j pi by 2 is minus j. So, minus j. So, the moment you got that, you can find out S11. S11 is V1 minus by V1 plus under this condition. Already we are here, so we are not written it explicitly. So, V1 minus by V1 plus, that is 0, because V1 minus is 0 here. And S21 is V2 minus by V1 plus, that is minus j. So, you got the first row, first column of S parameter. Let us see the second, for second column determination, you need to match terminate port 1, match terminated. Now, port 1 match terminated means V1 plus is equal to 0. The moment you see V1 plus is equal to 0, V2 minus also will be equal to 0. Now, in this case you are exciting from here. So, how much this V2 plus will be when it is coming here, that will be V1 minus. So, what is relationship between V1 minus and V2 plus? V1 minus is equal to e to the power minus j beta L V2 plus. Transmission line, wave moving from one end to another. So, once you have that, find out what is S22. S22 is V2 minus by V2 plus, V2 minus is 0. So, S22 will also be 0, and S12 is V1 minus by V2 plus, V1 minus by V2 plus, that is e to the power minus j pi by 2, that is minus j. So, now you put 0 0 minus j minus j. So, a transmission line has S matrix, that if the transmission line with characteristic impedance Z0, your reference impedance is also Z0, then there is no reflection at port 1, also at port 2 there is no reflection, but there is a transmission, that is why it is transmission line. But for a quarter wave line, you are getting both in the forward wave and or incident wave and reflected wave, they are getting a phase change of minus j. If you want to avoid that minus j, you will have to change the line, so that you can get a non quadrature thing, but this is the scattering parameter. Now, if it was asked you find out the z parameter of that, then you can use that formula we have given from S parameter, you can go to z parameter, but directly evaluating S parameter is easier, because this is a distributed line. Here wave picture is more prominent or more explicit, you can say. That is all. This type of problems as a microwave engineer you need to solve, so that to find S parameters of various circuits, networks, etc., and for measurement, your help is the network analyzer.